Ask why NVIDIA dominates AI computing, and you hear the same answer everywhere. A software moat, a flywheel, a $1 trillion valuation. All true, and it tells you almost nothing because it never says what was actually built. So here's the other version, not the market story, the machine. 11 specific engineering decisions stacked from a single processing core up to the data center sized fabric, each one solving the problem the previous one created. NVIDIA invented the first few outright. The ones it didn't invent, it spent billions to buy. Own all 11 and you can't be beaten by a faster chip. A rival would have to rebuild the entire stack at once. Here is that stack, one layer at a time. The mechanisms make the argument. Watch them assemble. It starts inside a single core, where a group of lanes runs one instruction at a time in lockstep, fast until the program hits a branch and the lanes want to split apart. The first move is making that GPU core run real branching programs. A SIMD thread group shares a single program counter. Every lane executes the same instruction at the same time, which is why the design is efficient. A conditional branch, though, asks some threads to take one path and the rest another. A pure SIMD machine can only follow one flow of control, so conditional breaks and returns are normally off the table. The fix is 3 pieces of state per group. An active mask says which lanes run the current instruction. A disable mask records why a lane is parked, waiting on a return, waiting on a break, or finished. And a call return sync stack holds tokens that remember a path the group still owes itself. The first such token is the sync token, pushed by an SSY instruction to mark where the group must reconverge. At the branch, the condition splits the group. Say 2 lanes take the if side and 6 don't. The hardware pushes a divergence token holding the not taken lanes and their program counter, sets the active mask to just the taken lanes, and runs the if side at reduced width. The other 6 sit masked off, waiting their turn. When the if side reaches the reconverge marker, the hardware unwinds the stack. It pops the divergence token, restores those 6 lanes as active, and runs the L side if they had skipped. The stack guarantees the deferred path is picked up exactly where it was left, no path is lost, and none is run twice. At the sync point, both sides are done. Popping the sync token restores the full mask and the group is back to full width SIMD. For conditional break and return, there's a shortcut. Instead of walking the whole stack, a diverging lane is simply flagged in the disabled mask, 1, 2, or 3, and re-enabled later when reaching matching call or pre-break token pops. So the core can run ordinary programs now, the foundation. But being able to run a program isn't running it efficiently. One thread waiting on memory can idle the whole core. Now, how to keep every execution unit working while some threads stall waiting on data? There are several different kinds of execution units. A math unit for multiply add, a texture unit with long memory latency, a special function unit for things like specialized mathematics. The threads are asynchronous, each one's current instruction needs just one of those units. If you let the threads hit the units directly, you'll get pileups on one unit while the others sit idle. And careless texture fetches trash the small texture cache. The fix starts with an instruction buffer. It holds one current instruction per thread, each tagged with the execution unit it needs, and each carrying an issue credit counter. With many threads buffered at once, the scheduler almost always has a candidate for every unit, which turns a traffic jam into a set of choices. Each cycle, the first stage is qualification. It throws out any instruction that would cause a stall. The unit it needs is busy, its scoreboard dependency bits aren't clear, an older instruction for the same thread is still pending, an in-flight load is waiting on the data cache, or a resource limit applies. What's left is the qualified set, only instructions that can issue cleanly right now. The second stage ranks the survivors. The central rule is the issue credit count. Every thread's counter goes up when it issues, so the thread with the lowest count goes first. A thread that's been stalled keeps its low count, so its priority quietly climbs while it waits, which means laggards catch up and execution stays close to launch order, balanced without forcing everyone into lockstep. A few instructions issue per cycle, filling every unit. Texture gets a special rule. The compiler splits a shader into phases. Blocks of math and textures are sized to fit the cache. At a phase boundary, no texture fetch, and the next phase is loaded to qualify until the current phase's fetches finish. So the next phase can't evade cache lines that are still in use. Math operations which don't touch that cache are free to run ahead. Now, nothing sits idle, but this still describes one fixed core, and the decisive move is what lets the same work run on hardware of any size. Move 3, the one that matters the most. Describe the work so it never assumes how much hardware exists. The idea begins with how you describe the problem. Instead of writing for the hardware, you decompose the work into a hierarchy. The whole problem is a grid. The grid divides into blocks, and each block divides into individual elements. Picture a high-definition frame. The image is the grid. A 16 by 16 tile is a block, and every pixel is an element. This hierarchy maps cleanly into a programming model. Each element becomes a thread. Each block becomes a cooperative thread array, a CTA, whose threads share data through fast shared memory and synchronize with one another. And each grid becomes a grid of CTAs. The crucial property, the CTAs within a grid are independent. None depends on another, so they can run in any order on any core. Independence is what makes the magic work. Hand the grid to a work distribution unit. It watches each core's ready signal, and the moment a core is free, it hands that core the next CTA. As cores finish, they are fed more work until the whole grid is done. The software never says which CTA goes where. The hardware decides. Now run the exact same grid on a different machine. A minimum system with one core executes the CTA in sequence. A medium system with 4 cores runs 4 at a time. A large system with 8 cores runs 8. The degree of parallelism is U times C times Q. More hardware finishes sooner, but every machine returns the identical result, and not one line of code was recompiled. Some problems have stages that depend on earlier ones. A fast Fourier transform, for instance. Independent grids can overlap freely, but when one grid needs another's output, a wait for completion barrier holds its CTAs until every CTA of the prior grid has finished. Dependencies are honored. Independence is exploited. This is the master stroke. Because the program no longer hardcodes the hardware, every future chip NVIDIA ships speeds up all the existing software with no rewrite. And software written this way runs only here. Invent this, and you have quietly logged the field to your platform. But it still tops out at a single processor. To go bigger, many must act as one, and NVIDIA's next moves are still its own. Private links that fuse its chips into one larger processor. That fusing starts with the link itself, a private, high-speed connection between chips, built so it never silently drops data. Lose a packet, and the link replaces it instantly, so the software above never sees a gap. Start with the obvious approach. To recover a lost packet, you stamp an ID tag, a sequence number into every packet. If one goes missing, the receiver knows exactly which to ask for. It works. But look closely. Each amber tag is a space that could have carried data. Tag after tag, you're spending bandwidth just to number things. So here is the better idea. Instead of numbering every packet, synchronize once. The link comes up by sending a single initiation packet. It carries the sequence ID of the first packet to follow. Here, number 1. Both ends load that value into a counter. Transmitter and receiver are now armed and agreed on where the stream begins. Now watch the counters. Every packet ships as pure payload, no tag at all. As each one leaves the transmitter, its counter ticks up. As each one arrives, the receiver's counter ticks up the very same way. They started in sync and move in lockstep. So both sides already know each other's packet IDs without it ever being sent. The packets are implicitly tagged for free. On NVLink, the unit being counted is the flit, a fixed 128-bit slice of a packet. But the links aren't perfect. Here, a packet is corrupted on the wire. Its CRC check fails or it simply vanishes. Either way, watch the counters drift apart. The transmitter moved on, but the receiver never counted the missing packet. That mismatch is the alarm, and the counter still tells the receiver the exact ID of the packet that went bad. The transmitter's timer expires with no acknowledgement, so it does something familiar. It sends an initiation packet again. Just like at startup, this resynchronizes both counters and now to the sequence ID of the first packet of the replay. Realigned, the transmitter resends the lost packet from its replay buffer. Its CRC passes, the receiver counts it, and untagged streaming resumes exactly where it left off. An ordered, lossless link lets two processors talk. The next step is letting one reach the other's memory directly. By default, reaching a neighbor's memory detours through a host in the middle, wasting the link that was just built. The old ways of using two GPUs are blunt. Alternate frame rendering hands each GPU a whole frame in turn. But that adds latency and breaks when one frame depends on the last. Split frame rendering struggles with modern workloads. What we want is finer-grained. Both GPUs sharing one frame at the same time with low latency. So the screen is diced into tiles, like a checkerboard. GPU 0 owns the teal tiles, GPU 1 owns the amber ones. Every triangle in the scene is sent to both GPUs, and each one simply clips away and discards whatever falls outside its own tiles. No wasted shading on the other GPU's pixels. But the rendering isn't that clean. To shade one of its tiles, GPU 0 needs a particular memory page, call it page P, and page P physically lives in GPU 1's memory. So GPU 0 reaches across the high-speed link and reads it. This works because the GPUs can access each other's memory directly. The catch: the link is slower than reading local memory. So GPU 0 needs that page over and over. Here is the clever part. A small hardware counter inside GPU 0 is quietly tallying every access to page P. The moment that count crosses a set threshold, page P is flagged as a hard page, and the GPU sends a notification straight to the driver. No software constantly checking. The silicon itself spots the hot spot. Now, successive frames tend to be nearly identical, so the next frame will almost certainly want page P again. Knowing that the driver schedules a copy, it moves page P out of GPU 1 and into GPU 0's own local memory ahead of time. A semaphore makes sure that the copy finishes before the rendering pass needing that page begins. Direct access works now, but it's slow if the data sits far from where it's actually used. Up till here, every layer was NVIDIA's own. Connecting these fused machines into a data center sized fabric is the part it didn't build, it bought it. Roughly $7 billion for one networking company in 2019, and years later, close to $1 billion for another's technology and team. That fabric's first job is to track which data is used where and move it closer to whoever is using it. Device A, say a network adapter, needs data that lives in device B's local memory, like a GPU's frame buffer. Two problems stand in the way. A uses its own internal addresses, which don't match the fabric's, and B can't pull all of its memory into the fabric at once. Routing every access through the CPU would solve it, but far too slowly. So B exposes only a small window of its memory to the fabric, a slice of shared address space mapped onto a few of its pages. Page P is visible through that window. Most pages are not. Meanwhile, device A keeps a mapping table, a cache that records which of its own addresses correspond to which fabric addresses. Right now, it's mostly empty. To reach page P, A doesn't guess. It sends a translation request to a translation agent, handing over its own untranslated address. The agent looks it up and replies with the fabric matching address. A stores that pair in its mapping table, so the next time it needs the same page, there's no round trip at all. Now, the real payoff. A takes its address, converts it using the cache translation, and reads page B straight across the fabric. Notice what isn't happening. The CPU never touches the data. No host software sits in the path. It's a direct device to device transfer, exactly the low latency path we wanted. But what about a page that isn't in the window yet? A's table has no entry, so the access would fault. Instead of failing, A sends the agent a page request. The agent reserves that page, exposes it through the window, and returns a fresh translation. A caches it, and the access goes through. And when B moves or reclaims a page, the agent sends an invalidation. A drops a stale entry and acknowledges. So through one small window and a translator, device A can reach all of device B's memory on demand with fast cache paths and a data plane that never touches the CPU. However, one processor's memory is still a bandwidth ceiling. No single unit feeds a large job fast enough. So stop relying on one memory, spread the data across many of them at once. A GPU's on-package memory is fast but small. Train a huge model or analyze a massive graph, you need far more than it holds. You could add more GPUs just to harvest the memory, but that's expensive and burns power. And reaching the CPU system memory or PCIe is simply too slow. The goal here is more memory, not compute. So we hang a pool of memory directly off the same fabric. Fabric attached memory modules reach just like a pure GPU's memory. The clever part is what runs them. Many use floor-swept GPUs, chips whose compute engines failed in manufacturing and would otherwise be scrapped. The broken compute is fused off, but the working memory controller and a couple of links survive, making a cheap, low-power controller that still speaks the full GPU language, including atomics. But there's a catch. A source GPU has many links. Each memory module has only a few. If the GPU's addresses fall in a regular pattern, every request can pile onto a single link, a hotspot, while all others sit idle. That chokes bandwidth down to a fraction of what the fabric could carry. The fix is to spray. The GPU runs a swizzle, an entropy function that scatters consecutive addresses across all of its links at once. Now no single link camps and none goes idle. The requests fan out to many modules in parallel and the GPU finally uses its full fabric bandwidth. Spraying creates a new problem though. Because it scatters only every nth address to a given module, the module's memory fills with holes, most of it wasted. So the switch does something elegant. It reverses the spray and divides the address down, packing those scattered addresses into a dense, gap-free range that fits the module exactly. Every byte becomes usable. To sum it up, salvaged silicon becomes an inexpensive memory pool. Spraying keeps every link busy. Compaction keeps every byte in use. The result? A GPU gains tens to hundreds of terabytes of fast fabric-attached memory with its ordinary load, store, and atomic model fully intact and not one extra compute GPU required. However, spreading data everywhere multiplies the addresses to translate, and one translator can't keep up or be trusted blindly. So, translation itself spreads across the fabric, and every request must prove it is allowed. Node A wants to use data that physically lives in Node B's memory. We would like them to share one large address space, so this is simple and fast. But these machines are often shared by many tenants at once, so a buggy or malicious process must never be able to read or corrupt another tenant's data. We need sharing and isolation together. Firstly, the owner publishes. Node B exports a slice of its memory into a global fabric linear address space, an address that means the very same thing on every node in the cluster. Its physical pages may be scattered, but they are gathered into one contiguous fabric linear address range, and the node decides exactly what it exposes. Now the requester subscribes. Node A writes page table entries into its translation buffer that map its own virtual addresses onto that exported FLA range. And critically, each entry is stamped with an affiliation identifier, the process, its privilege level, its security context. A single, very large page can cover the whole range at once. When a read actually happens, it walks a pipeline of address spaces. The source maps its virtual address to a fabric linear address and then sends the request across the switch. The destination maps that fabric address to a guest physical address and then to a system physical address, the real location and its memory. Four spaces, but to the application, it's one clean remote access. This is where isolation lives. Every request carries that affiliation stamp, and both the switch and the destination check it against the exported range. A request whose credentials match is allowed through, but a request from an unaffiliated process, the wrong ID, the wrong privilege, is denied right at the destination. One tenant simply cannot reach another's pages. And the FLA layer buys one more thing. It decouples the requester's view from the owner's reality. A single half-gigabyte page at the source can map to many small, scattered physical pages at the destination. So you get a vast shared address space described by very few table entries, with fragmentation hidden and isolation enforced in hardware. However, each cluster still lives in one tree, and big systems are built from many separate trees that can't address each other. To pool devices across those trees, each one needs a stand-in for the devices on the other side. A PCIe hierarchy is a tree. It fans out from a single root port on one CPU, so every device hanging off that tree belongs to exactly one server. Letting another server's hierarchy reach across to use that device means crossing trees, and plain PCIe simply forbids it. The industry's earlier answer, MRIOV, was defined for this but never caught on. So the switch introduces a ghost device. To host A, it looks like a perfectly ordinary PCI device. It has a real device ID, its own bar memory window, and tag space. But it runs no actual function. It exists only to stand in for a device that really lives in another tree. Pair a ghost in one hierarchy with a real endpoint in another, and the two trees can finally be bridged. When host A writes a transaction layer packet to its ghost device, the switch parses it and compresses the source ID into a compact policy group. Then it matches policy group plus destination against a fast lookup table. Address routed packets match on destination address, ID routed packets on destination ID. The winning entry decides what happens next. The matched rule rewrites the packet so it belongs in the second hierarchy. The source ID becomes the target ghost device's ID, the destination address is remapped, and the traffic class can also change. Now the write lands in the target tree looking exactly as if a local ghost device had issued it. Content delivered across hierarchies with no change to the real device. Reads are harder because they are non-posted. A completion has to come back. So the switch allocates a fresh tag and rewrites it, letting a host's unpredictable tag be tracked across the bridge. When the completion returns, tag tracking restores the original requester ID and tag, and the read finishes cleanly back in the first hierarchy. Through paired ghost devices and this match, rewrite, and tag pipeline, hosts and endpoints in completely separate PCIe trees talk as if they were neighbors. One physical device can be shared across many servers, true disaggregation, higher utilization, and no modification to hardware itself. However, all this movement floods the receiving end. The intake itself can become the bottleneck. So the receive path has to absorb traffic at full speed without ever stalling the processor waiting on it. Classic generic receive offload coalesces a flow's packets right in the NIC. The trouble is twofold. First, it holds and stalls those packets in hardware until a timer fires, usually a full round trip, which bakes a mixed latency penalty into every batch. Second, the NIC has only a small fixed set of hardware contexts. With thousands of flows interleaved, they collide and flush, and the coalescing efficiency collapses. Adaptive GRO moves all the queuing out of the NIC and into host memory, keeping only a tiny per-flow context on the card. Each arriving packet is parsed, classified into its flow, and split into a header and payload. And crucially, neither one is modified. The headers trim into a per-flow header buffer. The payloads are placed straight into application buffers. The packets are never held in the NIC. They keep moving. Because nothing waits on a timer. There is no artificial latency since a context is just lightweight metadata. The card can track millions of flows at once without collisions. The NIC links each flow's headers into a forward chain and posts a completion entry, a GRO ID pointer to the first and last header, the aggregate length, a checksum, and the starting sequence number. With that, the host processes just the first and last header and skips every one in between. Full coalescing efficiency, but on host's own schedule with no fixed wait. Because the real order of moves no longer matters once it's reconstructed, recovery is just arithmetic on TCP sequence numbers. Aggregations are arranged by sequence range, and a gap from a dropped or a rerouted packet simply waits. When the late payload finally arrives, it grows an aggregation at its low or high end, even merging the two into one. So the data is recovered without flushing the batch. To sum it up, packets stream continuously to the host. A tiny context supports millions of flows without collisions. The header chain lets the CPU skip the middle of every batch, and the sequence math absorbs reordering and drops. Full coalescing efficiency with no NIC stall, no fixed latency, and no packet modification. Now, one question remains: how it crosses the fabric, because a single jammed or a broken path stalls everyone. So, routing can't be blind. It reads each flow, spreads load across the healthiest routes, avoiding failures instantly. A modern data center fabric, like a fat tree, offers many equal cost paths between any 2 points. Spreading traffic across them is how we get full bandwidth. The trick is choosing well, and the usual method, a blind hash, often chooses badly, and here's a better way. The standard equal cost multipath picks a path by hashing a packet's header fields, and it does this right at the edge switch, with no view of the rest of the network. When a few large, unequal flows are in play, the hash can pile up several of them into one link, overloading it while the others sit idle. And when a link fails, ECMP has to reshuffle everything that was using it, which breaks the existing balance and can cause flapping. The fabric adapter reads more than header fields. From one buffer, it takes the packet header. From a second buffer, it takes control information like a live picture of the network congestion and choke points, together with the application's own state like flowlets and which data blocks are safe to reorder. That control information is fetched through a scatter-gather pointer so it can live anywhere in host memory. A packet classifier groups the header. An application and network-aware state function turns the control information into insight. Together, they feed a hash and resolve load balancer, which produces an index into the routing table. Choosing among the equal cost links is not by luck, but by which one is actually free and at the granularity of the application data rather than whole network flows. The routing table row resolves to an ECMP group, and the path selector picks the least loaded port in it, the quiet link, not the congested one. It muxes the header back together with the payload and forwards the packet. Done across every flow, the load now spreads evenly instead of collapsing onto a single path. For failures, the controlling hosts pre-compute alternate routes and hand the adapter an alternate failure route index as a scatter-gather element. So the moment a link fails, the path selector overrides to the pre-computed alternate at once. No waiting to rehash every flow, no flapping, and minimal packet loss. To sum it up, the adapter balances on real network and application state instead of a blind hash. So equal cost links stay evenly loaded, big flows stop colliding, and failures reroute through pre-computed alternate routes instantly. The result is higher throughput, fewer hotspots, and graceful failover. Now the fabric balances itself and survives a broken link. That's the 11th move and the last piece of a machine where thousands of processors behave like one. Step back, and the dominance stops looking like a mystery. NVIDIA invented the GPU core that runs real programs, the scheduler that keeps it busy, the programming model that lets one program scale to any chip it'll ever ship, and the private links that fuse a rack full of those chips into one larger processor, locking the platform. Then it bought the data center fabric that ties thousands of those chips into a single machine. To displace it, a competitor doesn't need a faster chip. It needs all 11 layers, plus the years of software written against them at the same time. That isn't a moat you cross. It's a machine you would have to rebuild. Thank you.